The talk I wanted to do is a talk I've done many, many times before. It's called the Three Laws of Test-Driven Development, in which we are going to discuss the discipline of test-driven development, and I will also do a small demo, and I will use the Kotlin language for that demo. Three laws of TDD. What is test-driven development? Well, first and foremost, test-driven development is a discipline. And like all disciplines, it has arbitrary elements to it that many people might find frustrating or inexplicable. So, for example, surgeons, when they wash their hands before doing surgery, they do not simply walk into the scrub room and wash their hands the way you or I might. They have a discipline. They follow a ritual. And that ritual is fairly involved. For example, they might get a brush, and that brush they will use a certain kind of soap on. And then once the brush is soaped up and their hands are properly moistened, they will stroke their fingers 10 times on one side of the finger with the brush, and then they will stroke that same finger across its top 10 times, and then the other side of the finger 10 times, and then the face of the finger 10 times, and then the nail 10 times, and then proceed to the next finger. And you can imagine why they follow a ritual like this. They want to make sure their hands are clean, that all the bacteria have been removed. But notice that there are arbitrary elements here. Is 10 the right number? Could it be 8? Should it be 12? Do they have to divide their finger into the 4 quadrants? Or could they just do it with 3 quadrants? There's this element of arbitrariness. And that's also true of test-driven development. It's true of all disciplines. All disciplines have this essential nature, got to get your hands clean, but there's also this arbitrary element, 10 times. So, test-driven development. I have broken test-driven development up into 3 laws, and those 3 laws are somewhat arbitrary, but I believe they define the discipline pretty well. These 3 laws seem stupid to most developers. If you've been a developer for any length of time and you start looking at these 3 laws, you'd think, well, that's nuts. I don't want to do that. And as an example, let me quote you the first law. The first law of test-driven development says that you are not allowed to write any production code unless it is to make a failing unit test pass, which means you must first write a unit test, and that unit test must fail before you can write any production code. Now, right away, this just sounds dumb. I mean, what are you supposed to test? There's no code there. How can you write a test for something if the something doesn't exist? So that's the first arbitrary thing in test-driven development, and it gets many developers put off. They think, I don't make any sense out of that. But the worst is yet to come, because the second law makes things much worse. It says you are not allowed to write more of a unit test than is sufficient to fail. As soon as the unit test fails, you have to stop writing it. You can't write the whole test. You have to stop writing it as soon as it fails. And oh, by the way, failure to compile is failing. So the instant the unit test doesn't compile properly, you have to stop writing it and start writing production code. Now, since there is no production code to begin with, the unit test is probably not going to compile very quickly. You're going to type two or three words. You may not even finish an entire line, and you'll see a compiler error, and you have to stop and start writing production code. So this is much worse than just the first law. And if you're a developer, you think, well, how am I going to get anything done if I'm going to write a couple of characters of a test and then have to switch and write a couple of characters of production code? But then the third law kicks in, and it's the worst of them all. And it says you are not allowed to write any more production code than is sufficient to pass the currently failing test. Now, this is going to lock you into a cycle that is 5 seconds long. You will have to write a unit test first because the first law says you have to, but you're not going to be able to write much of it because it won't compile. So then you'll have to write some production code, but you can't write much of that because that'll make the unit test compile. So you'll have to go back to the test and add a little bit more to that, and that won't work because it won't compile again. And you'll have to go back to the production code, and you're going to be switching back between these two streams of code on a 5 second by 5 second basis. And most developers, especially if they have a lot of experience, think of that as being crazy, stupid, boring, tedious. I mean, you would never be able to finish an if statement or a while statement. You'd never be able to complete your thought. You would always be interrupting yourself. And that's a reasonable way to think about it. It does sound goofy. It, by the way, sounds just as goofy to senior developers nowadays as washing hands sounded to doctors in the early 1800s. Because back in those days, no one understood germ theory, and the idea of washing your hands seemed silly, stupid, boring, tedious, a time waster. Took a very long time for surgeons to realize that cleaning their hands was actually kind of important. So, what if a group of us followed these 3 laws? What would happen? What if we had a room full of people and those people were following these 3 laws? What would you observe about that room full of people? Walk through that room. Pick any one of the people in that room following the 3 laws. Doesn't matter who you pick, and it doesn't matter when you pick them. Everything they were working on executed and passed all its tests within the last minute. And it doesn't matter who you pick, and it doesn't matter when you pick them. Within the last minute, everything they were working on executed and passed all its tests. What would your life be like if a minute ago everything worked? And this was always true. It was always true that everything worked a minute ago. What would your life be like? How much debugging would you do if everything worked a minute ago? And the answer to that is fairly clear. You wouldn't do an awful lot of debugging if everything worked a minute ago. There's not a lot to debug in a minute's worth of coding. In fact, the most common debugging technique amongst test-driven developers is to hit Control-Z enough times to make the test pass again, and then to rewrite the code you just wrote. How many of you are good at the debugger? How many of you have the hotkeys in your fingers, the debug foo in your body? You know how to do breakpoints and step intos and step overs, and you can set breakpoints and watch points, and you can really debug. This is not a skill to be desired. You don't want to be good at the debugger. The only way you get good at the debugger is to spend a lot of time debugging. And I don't really want you to spend a lot of time debugging. So I want you to spend a lot of time coding. Now, do I use a debugger? Yes, I do. The one in IntelliJ is very nice. I use it all the time. But I don't use it for long periods of time. And I don't use it as a part of my daily coding exercise. The amount of time I spend in the debugger is very small. And usually it occurs when I've got some test that's failing and I don't exactly know why, and I set a breakpoint on the failing test and I step in a couple of times and it takes me right to the code and I see the fault immediately and go, oh yeah, okay, and I fix it. The amount of time I spend in the debugger is small enough that I can't remember which hotkeys are step over and step into. It's F7 and F8, but I don't remember which one is which. And I always have to hover over the little icon and remind myself. It's just not in my memory. That's the level the level of familiarity I think you want to have with the debugger is something that you are tentative about rather than something you are expert at. Now, I don't want to tell you that you don't ever use a debugger. I use a debugger, as I just said. And there are times when you have to do long, horrible debugging sequences because this is still software. It's still hard. Weird things still happen. But the incidence of that, if you are a test-driven developer, is much smaller than if you are not a test-driven developer. So I could tell you that you could cut your debug time by some factor, call it D for debug time. And I'm not even going to tell you what that factor is, just D. Does this time that you are saving by not debugging make up for the cost and the silliness of the three laws? Hold that thought because there's something else to consider. How many of you have integrated a third-party package? Most of us have, and when you integrate a third-party package, you have to get it from somewhere. It's probably a zip file or something. You get this zip file and you unpack it, and sure enough, in the zip file, there's some directories that have libraries in them. Maybe it's class files, or maybe it's jar files, or maybe it's even source code. Somewhere in that directory structure, there's going to be a PDF, a manual, written by a tech writer that describes the way that this module works and how to integrate it. And at the back end of this PDF manual, there's an ugly appendix that contains all the code examples. Where's the first place you go? Well, you're a programmer. You don't want to read what the tech writer wrote. You want to see the code. So you probably go right to the end of the manual, find the code examples, and read them and understand them, and that's how you learn how to integrate the third-party package. When you are following the three laws of test-driven development, what you will produce in the unit tests are the code examples for the entire system. The same ones that you would have gone to at the back end of that PDF, the code examples for the whole system. That's what unit tests are. They are little snippets of code that explain how certain parts of the system work. And because you're doing test-driven development, there is a snippet in there that explains how every part of the system works. And these unit tests do not know about each other. They are not interconnected. Unit tests do not form a system. They are independent little units of code that reach into the production code and exercise a very limited part of it. And therefore, they are easy to read and easy to understand. And if you want to know how to work some part of the production code, there's a unit test that will tell you exactly what to do. Exactly how to call the functions, what arguments to call, what exceptions to catch. If you want to know how to create some object, there's a unit test in there somewhere, probably a set of unit tests, that create that object every way it can be created. And these documents that describe how to work the system, because that's what these tests are, they're little documents, are written in a language that you are intimately familiar with, very comfortable with. That language is so formal it executes, it's utterly unambiguous, and it can't get out of sync with the production code. It is the perfect kind of low-level documentation. It's code, and that's what programmers want to read. So if you follow these three stupid laws, you will inevitably produce a stream of documentation that covers the entire body of the production code in a perfect way for developers to interpret. Now, does that make it worth to follow these three laws? Well, hold on, because there's another thing to consider. Probably many of you have written unit tests after the fact. And if you have, because it's the most common way of writing unit tests nowadays, if you have, you probably also discovered that it's not a lot of fun. And why isn't it fun? Why isn't it fun to write unit tests after the fact? And the answer to that is pretty simple. You already know the code works. You already know the code works because you've tested it manually. And now you have to write a bunch of unit tests after the fact, which seems like a waste of time because you already know the code works. But you're supposed to do it because some process person said, oh, yes, you must write unit tests. And so you kind of half-heartedly go in and write a unit test here and a unit test there. And you look at the unit test, it sort of works. You do another unit test, yeah, that one works too. Inevitably, however, you will come to the code that's hard to test. It's hard to test because you did not design it to be testable. And the effort required to make it testable seems too large. And you look at your watch and you say, oh, heavens, I've got other things I've got to do, and I already know this works. I don't feel like spending the time in making this function testable, and you walk away, leaving a hole in the test suite. And you know that if you leave such holes in the test suite, so do other people. So you look at the rest of the team and you realize the rest of the team is also leaving holes in the test suite, and therefore the test suite is full of holes. Now, what is the result of a test suite that's full of holes? When you run a test suite that's full of holes, if that test suite passes, it tells you nothing. It does not tell you that the system works. There is no decision you can make if that test suite passes. If it fails, it tells you something. Something you tested broke, and that's valuable. But if the test suite passes, it tells you nothing. And of course, you always want it passing, so it constantly tells you nothing. You don't trust the test suite. How many of you have had this experience that you run the test suite, you see it pass, and then you kind of smirk to yourself and say, yeah, it passed. And you know that there's no action you can take just because it passed. Something different happens when you write your tests first. When you write your tests first of all, it's fun. And why is it fun? Well, it's fun because you write something that doesn't work and then you make it work. And most of us programmers got into this business because once in our very young lives, we wrote something that didn't work and then we made it work and we felt the power. And we want that power and that feeling again of constantly making things working. Every time you write a little unit test and you see it fail and then you make it pass, you get this little jolt of, oh yes, I'm a programmer feeling. So it's fun, or at least more fun than writing tests after the fact, but there's something else. If you write the test first, it is impossible to write the function that's hard to test. You can't write the function that's hard to test because you wrote the test first. You have to design all of your functions to be easy to test because you're writing the test first. And a function that is easy to test has another attribute. The reason it's easy to test is because it's decoupled. That's what it means to be easy to test. Something is easy to test if it's not coupled strongly into the rest of the system. So by writing the tests first, it's fun, but you also produce production code that is much less coupled. You will decouple it in ways that you never thought you would decouple it. But then something else happens. And this is the real reason that we do test-driven development. I'm about to tell you what that is. All that other stuff, the fact that you reduce your debug time and the fact that you produce documentation and the fact that you produce better code and it's fun, all of that stuff is fine. It's good. We like it. But the real reason that we do test-driven development is because if you do test-driven development and your test suite has been produced by test-driven development, then when the tests pass, it means something. It means that the system works. It means that you can ship, you can deploy. And that's really the goal of test-driven development. The goal of test-driven development is to create a test suite that when it passes, tells you that you can deploy. There's nothing left to do. There's no other tests that need to be run. You are ready to deploy because the test suite runs. How many of you have looked at your screen and seen bad code there and had that bad code slow you down? How many of you have been slowed down by code that is a mess? And at this point, you're all nodding and saying, well, yeah, I have. And if you haven't, then either you're not a programmer or you're lying to yourself, because we have all been slowed down by bad code. The question then is, why did we write it? Why did we write this code that's bad? And the answer to that has a number of interesting factors to it. Number one, we often write bad code because we're in a hurry, we're in a rush, we've got deadlines, we have to go fast. And so we write the thing that slows us down in order to go fast. I will leave you to deal with the logical inconsistency of that. There's another reason why we write bad code, and that's because it's impossible to write good code at first. We're so focused on getting the problem solved that we solve the problem by virtually any means, leaving a mess in our wake, and then we do not go back and clean it up. Why don't we go back and clean it up? Well, for one thing, it'd take a lot of time, and we don't have that time. We've got deadlines. But there's another factor, a much worse factor. How many of you have brought code up on your screen? You look at it and you think, oh, God, this is a mess. I should clean it. And your very next thought is, I'm not touching it. Because you know if you touch it, you will break it. And if you break it, it becomes yours. So you walk away, not cleaning the code. I submit to you that if that is your reaction, if you respond that way to the messy code on your screen, then the only thing that can ever happen to that code is that it will rot. It will get worse and worse and worse over time, because no one can clean it. Everyone backs away. And so the only thing you will ever do to it, even though you're adding features and fixing bugs, you will do so in a way that preserves your own safety, not the cleanliness of the code. You will respond in fear, and you will rot that code, and it will get worse and worse with time. And as it gets worse and worse with time, the whole team slows down, because that bad code slows everyone down, until you finally get to the point where the code is so bad and so awful that all the developers are demanding that the whole thing be redesigned. But what if you had a test suite that you trust? A test suite that covers everything. A test suite that when you run it and it passes, you feel confident you can deploy. Then you bring bad code up on your screen, and you look at that bad code, and your first thought is, I should clean it. And your next thought is, I bet I could change the name of that variable right there. And you do, and you run the test suite, and oh, it passed. By the way, that test suite's going to have to run fast. So then you say, oh, that function's too large. I think I'll split that function in two. That'll clean it up a little bit. You run the test. Oh, it passes. And then you say, oh, I'm going to take that function down there. I'm going to move it to a different class. And you run the test suite. And it fails, and you put that function back. And you realize what you did, and you do it the right way, and it passes. This is the way we want you to behave. We want you to have control over the source code. We want you to be able to reach into that source code and clean it on a whim without a second thought. And the reason you can do that is because you have that test suite. And that test suite runs fast. And the result of that test suite, when it passes, allows you to make decisions. Decisions like, I will clean the code. Okay, enough of my preaching. I'll come back and preach some more. At this point, you probably want to see this in action. If you've never seen it in action, fine, I will help you with that. I'm going to do a little demo. The demo will be in Kotlin, so I'm going to create a Kotlin project here. Once I get my browser up, there's IntelliJ, good. And I'm going to create a little project here. We're going to do the prime factors kata. This is one of my favorite demonstrations. So I'm going to create a Kotlin module. And let's see if I can remember how to do this. Oh, yes, that should be fine. Factors, prime factors, we'll call it. Up comes my little workspace. Lovely. And let's go here. We're going to create a package named prime factors. Good. And inside that package, we're going to create a Kotlin file named prime factors test. And over here, you see I've got this little pop-up. This is really important. If you don't do this, you're going to have trouble. Configure your module, which you do that by clicking on this little link here, and it'll pop up the module area here. And this is so that the runtime library is brought in. And I don't bother to copy it. I just use the library from the plugin, so I'll just do that. That should make everything work just fine. Okay, now I'm going to do prime factors. Class prime factors test. Oh, look at that. I already knew what it wanted to call it. That's because of the name of the file. I'm going to write a test. This is a unit test. Nothing. Now, some of you may be looking at this and saying, gee, that looks a lot like JUnit. Well, yes, it does look a lot like JUnit, and that's because it is JUnit. Kotlin works very well with Java, and what we're actually doing here is we're using the Java JUnit library. Although notice that this is red here, and the reason it's red is because I don't have the JUnit library in my path. So I'm going to go to the modules here, and go to my dependencies, and I will go find my JUnit library, which is somewhere up here in this horrible directory structure. This is one of my complaints about IntelliJ. I wish there was a better directory browser. Oh, yes, here it is. Good. That one and this one, I'm going to take JUnit and Hamcrest both. Bring those in. Good, lovely. Now it should know what this is. Does it import it? Yes, it does. It brought it in from JUnit. That's nice. I should be able to run this. Let's see. How about that? A little bit of build time, and then boom, we're up, and we've got a test suite running. This is the way I start every project. The first thing I do in every project is get a nothing test to run. Now, what are we writing? We are writing a little tool that will calculate the prime factors of an integer. So you hand it an integer, and it'll tell you what the prime factors of that integer are. I wrote this long, long ago because my son came home from school with homework, and I wrote a little thing that would allow him to check his homework, and I did it test-driven, and I use that now as this exercise. So we are going to repeat what I did so long ago at my kitchen table to help my son with his homework. I'm going to write a test called factors. I'm going to break a few rules here. I'm going to write all the tests in a single test function. As you get more and more familiar with test-driven development, you'll realize that that's a slight breaking of some of the rules. It's a breach of etiquette, but it makes this a little easier to read. So I'm going to do it for your benefit. Let's see. I'm going to invoke Hamcrest here. Assert that factors of 1 is okay. The prime factors of 1 are nothing. There are no prime factors of 1 because we don't count the 1 itself. So this should be an empty list. And we're going to use the empty list function from the Kotlin library. A bunch of red here. Let's get this straightened out. We're going to put the appropriate prefix on assert that. Now we can import that, or JUnit, good. Now I can do the import static, that's nice. I can create the factors of function, which I will create right in here. Let's see, call that n. I'm going to say that's a list of int. That's the integer in Kotlin. Yeah, silliness. Okay, good. So factors of will be a function that takes an integer in and produces a list of all the prime factors of that integer. Good. It's going to have to return something reasonable, so we'll have it return an empty list. Good. And our assertion here, well, is, notice the little backticks. That's there because is actually a keyword in the language, but you can use the backticks to escape that keyword. The is function comes from Hamcrest. So org.hamcrest.corematchers.is is the name of this function. And now I'm going to statically import that so that I don't have to see that all the time. Oh, there we go. Looks like it all compiles. Let's see if it runs. Oh, yep, this runs good. So I'm going to assert that the prime factors of 1 produces an empty list, and that works because the factors of function produces an empty list. Good, excellent. So next test. Did that wrong. It should be that. Good. Factors of 2 is, okay. The prime factor of 2 is just 2, so it's going to be a list of 2. List of is a standard Kotlin function in the library that produces a list with just a 2 in it. It's kind of nice. This should fail. It does fail because we expected a list with a 2 in it, but we got an empty list. So this is the list that we expected. This is the list that we got. Okay, we can make that pass by taking this empty list and putting it in a variable named factors. And we will declare that variable with a var. Actually, it doesn't need to be a var. It can be a val. The difference between a val and a var is that vals are immutable and vars are mutable. And our list, our factors list, is oddly going to be immutable, even though we can add things to the list. So we'll come to that later. You'll see it happen shortly. Now I have a list of factors, and in order to get 2 to be produced, I need to say something like this. If n is greater than 1, well, then it's probably 2, because that's the only test I've got. Factors.add 2. This looks just like Java. That's because it pretty much is Java. But notice the add doesn't compile. Why not? Well, because empty list produces an immutable list, a list that can't be changed. And so the compiler says, oh no, you can't add to a list that can't be changed. I can fix that by returning a mutable list of nothing. Still an empty list, but now it's mutable. Notice that makes it compile. I believe this will pass. Yeah, excellent. I've made it pass. Lovely. I'm a programmer. All right. Let's do 3. Factors of 3. Oh, 3. Good. Is a list of 3. Well, this is really easy to make pass, although it might seem difficult at first. It turns out to be trivial because you can take that 2 and turn it into an n. And if you think about that for a minute, you'll realize that'll pass all the existing tests. Okay, fine. Next. Factors of 4 is a list of 2 and 2. Okay. Well, how do we get that to pass? I think I can do it this way. Inside this if statement, if n is divisible by 2, then what we want to do is put a 2 in the list, no semicolons, and we want to reduce n by 2, by a factor of 2. So n divide equals 2. And that would take our 4, this is the 4 that we're passing in, this will take our 4 is divisible by 2, it'll put a 2 in the list, it'll turn that 4 into a 2, and then it'll put the other 2 in the list. So that should work just fine, except that it won't compile. Now why won't it compile? Well, it doesn't compile because arguments to functions are not mutable, and I'm trying to mutate it here. And it would be interesting if I could do this to say that the argument is mutable, but the language doesn't seem to allow that. Maybe there's some trick I don't know yet. So what I'm going to have to do is introduce a new variable. I'm going to do that this way. I'm going to change the name of the argument temporarily to nn. Then I'm going to say var n equals nn. That will create a variable, something that is mutable, and now all these references to n are mutable. You can see they're mutable because they're underlined. IntelliJ does this nice thing of underlining everything that's mutable. This should work. Oh, heavens, it fails. Oh, but look at why it failed. This is the 2 case. This is this test here that's failing. And it's failing because it expected a list with a 2, but it got a list with a 2 and a 1. Where did that 1 come from? Well, that 1 came from right there, right? Because we took the 2 in. Oh, that's divisible by 2. We reduced the 2 to an n, 2 to a 1, and we put the 1 in the list. So we don't want to put the 1 in the list. We can do that by saying only put n in the list if it's greater than 1. All right, now that should pass. But we've made a bit of a mess here. We need to refactor a bit. NN and N are terrible names. So what is this N? Well, this N is the remainder after you remove all the factors. So let's change that to remainder. That's nice. And now we can take our N, and we'll just make that N again, because it's the number that's coming in to be factored. And I believe that will still work. Oh, good. And, okay, oh, look at this if statement here. This if statement has the same predicate as that if statement, and it comes right after it. That's weird, isn't it? It kind of looks like there ought to be some way to combine those two. I can actually make it weirder by taking the if statement and moving it outside of the first one entirely. This one will still pass. Think about why it still passes, but now notice I've got 2 if statements at exactly the same level that have exactly the same predicate in them. That's interesting. Why is it interesting? Well, you're about to see why. Because, first of all, we're going to do a few tests, and you'll find this interesting if you've never seen this before. The factors of 5 are a list with a 5 in it. Excuse me, list of. And this will pass because 5 is prime. It means it's not divisible by 2. So we fall through right to here and we add it. Okay, so that factors of 6 is a list of 2 and 3. That list of. I'll get that right. This will fail. Oh, no, it'll pass, won't it? It'll pass because 6 is divisible by 2, and there will be a 3 left over. Okay. That factors of 7 is list of just 7, and that will pass because 7 is prime. Oh, lovely. Good. 3 in a row, guys. 3 in a row. You know, where'd this algorithm come from? And it's already done a whole bunch of them. It can factor from 1 up to 7 already. Let's see, that factors of 8 is a list of, okay, 2 and 2 and 2. All right, that's going to break everything, isn't it? Because now we've got 3 factors, and nothing we've done can put 3 things in the list. How do we get this one to pass? And here's where life gets very interesting, because we can take that if and turn it into a while. That makes it pass. We continue to factor out 2's as long as it's divisible by 2. And that makes it pass. Isn't that interesting? Okay, so now let's do 9. Factors of 9. List of 3 and 3. Those are the 2 prime factors of 9. This will fail because we don't factor out 3's yet. Now, I can factor out 3's by taking this loop right here and copying it. You dog. Okay, there we go. Good. Copy it. And then taking all of the 2's and turning them into 3's. And that should factor out all the 3's. That works. It's also hideous. That's a terrible way to solve this problem. If I solved it this way, I'd never completely solve the problem. So I've got to get rid of this, although it gives me the clue of how to really solve it. What I really need to do is take this while loop here and put it into another loop. Before I can do that, though, I've got to take that 2, turn it into a variable, all 3 instances, please, which I will call divisor. Lovely. And I will take divisor up out of the loop. I will now turn this if statement, get ready for this, you're going to really like this. I will take that if statement and turn it into a while statement because I want to continue looping until the remainder has been reduced to 1. Right? You divide through by all the factors, you're going to get a 1 in the end, aren't you? But I better increment that divisor. I'll do that here. And, I can't increment the divisor because it's a val. I got to make it a var. There we go. Notice it underlined it. Isn't that nice? Run my tests. Oh, test pass. And what is the terminating condition of this while loop is when remainder is equal to 1. That's what this is going to do. It's going to turn remainder equal to a 1, which means this if statement will never get executed. It's really the terminating condition of the old while loop. Excellent. Good. Gosh, I think we have an algorithm, don't we? Let's see if this algorithm works. Factors of 2 times 2 times 3 times 3 times 5 times 7 times 11 times 11 times 13. Did I type that correctly? Good. Yes. Is 2, 2, 3, 3, 5, 7, 11, 11, 13. I typed that correctly. Looks like I did. Oop, I forgot the list of. Is a list of good. Yep. So, yep, good. Let's just line these up so you can see they're the same. Look the same. 5, 7, 11, 11, 13. Yep. Does that work? And, of course, it does. We are done with the algorithm. Now, the interesting question here is, where the heck did that algorithm come from? Because I didn't design it up front. I didn't think it through up front. I didn't plan out a way to solve this algorithm. What I did is I just posed a bunch of test cases, and one by one I made those test cases pass. And somehow this algorithm came out. I'll leave you to ponder that. It's one of the more interesting elements of test-driven development. Apparently, test-driven development is a way to incrementally derive solutions to problems. That doesn't mean we don't plan things. It doesn't mean we don't design things. It doesn't mean we don't do architecture. It does mean, however, that we've got a tool or a discipline that supports incremental development of algorithms. And with that, I'm going to stop my talk and my demonstration and open this up to questions, because I see there are a bunch of questions on the list, and I believe my plucky assistants are going to be picking those questions for me. So, what questions do you have, and how can I answer them?
Okay, so the first one is, how would you approach this problem if being asked how to use TDD along with randomized testing or even more general approaches like property or model-based testing?
So in functional languages, there are these interesting test frameworks that allow you to specify a very rigorous type structure, and then the testing tool will invent random values that fit into that type structure. And that constrains the number of values that the tests can then feed into your application, and your application should be able to deal with them all. Very useful tools. If you've got a tool like that, like FSCheck or QuickCheck or something like that, I strongly urge you to learn those tools and take advantage of them, because they're very powerful. Is that what I'm doing here? No, I don't have any randomizer here. Could I have invented a primitive randomizer in order to do some of these tests? For the prime factors problem, probably not. But for other problems where the value of a number is not quite so important as the fact that it is a number, or the value of a set of fields is not quite so important as the structure is, then I have done some primitive random creations that can be useful sometimes. And then you can iterate like 100 times. You can say, give me 100 instances of random values, and I'll plug them into my unit tests. There's still unit tests. There's still property tests. And some people try to make the distinction between unit tests and property tests. I look at them and say, well, a property test is really just a unit test that accepts a bunch of values. So I think that's a perfectly valid thing to do, and you should learn how to do it.
Okay, next question from Dave. No problem with what you say, but sometimes you start working on an existing code base and want to improve it. Do you use some of the tactics from Michael Feathers?
I do. And so Michael Feathers wrote a book, and the name of that book is Working Effectively with Legacy Code. One of the most depressing books you might ever read, because it makes it very clear that there is no easy solution to this problem, no quick fix to legacy code. It is very difficult to take a very large wad of legacy code and bring it under the kind of control that test-driven development would give you. It is a long and a frustrating task. That doesn't mean it's not worth doing. I just want to make sure you understand that there is no quick fix here. To get a bunch of legacy code under the kind of control that test-driven development will give you is a task of months and probably years. The benefit, however, is that as you are gaining more and more control over this code, your life does get incrementally better and better. So you may not be able to run the whole test suite and trust it, but you will eventually get to points where you can run segments of the test suite and trust that. There's a whole discipline for doing this, for taking a wad of legacy code and gradually getting it under control. And Michael's book is a great introduction to that particular discipline. There are other people who have done talks on this. I have done talks on this. It's probably not appropriate in this minimum amount of time that we have here to go into that discipline. Suffice it to say, however, that there is a discipline that will help you get through the legacy code issue.
Okay, so from Michael Marigal, he says, you're talking the tests should run fast, and this is what everyone was saying for many years, but now a lot of developers are moving from fast class level tests to more like functional tests that are starting embedded web containers and testing REST APIs. Those tests check much more out, and at the same time much smaller. What is your take on that? And this, I think, goes in line with someone else that is also asking, saying, do you consider long compilation times an obstacle for TDD? So they're both somewhat talking about speed.
Yes, so long test times and long compile times, long build times, are obstacles to test-driven development, and they are obstacles to software engineering in general. Anytime you put a long lag into a feedback loop, you lose control of the thing that you're trying to control. It's just the way control theory works. Our goal as software developers should be to eliminate or drastically reduce any of those lag times in the feedback loop. So tests need to run fast. I understand that people try to do, long testing through REST APIs. There's nothing wrong with testing a REST API. The fault or the mistake that people make is that they test business rules through the REST API. When you're going through a REST API, what you should be testing is that the API communicates properly with the internal module, and then run a series of unit tests on the internal module that test all the business rules. And those can be done fast. Any test that slows you down needs to be looked at and addressed. So, for example, you don't need to test a REST API, each faction of the REST API, more than once. Once you know that the API can take apart the REST strings and identify the variables and so on, once it can convert that HTTP request into a data structure, you know that REST API is working as an interface. You don't need to test that more than once. Then you can write unit tests that test the individual functions inside your module. If you test all your business rules through the REST API, you are executing all of that conversion code and all that socket management code and all the HTTP request response cycle over and over and over again worthlessly. Don't do that.
Okay. There's a couple of questions in line with mock objects and Mockito and that, and they're all basically asking the same thing. Like, what is your take on mock objects, and how do you do TDD with mocks or using platforms like Mockito?
So I love the mocking tools. I think they're very, very powerful and very interesting. I have used Mockito and JMock and EasyMock and lots of other tools like that. What I find, however, is that for most of the mocking I do, I write my own. And especially if you're using IntelliJ, it's just remarkably easy to point at a Java interface or a Kotlin interface and just say generate it for me. And it'll automatically generate it as a nice little stub, and then you can reach into that stub and add just the right code you want. And you don't have to put the horrible dots and parentheses kind of thing that EasyMock or Mockito forces you to do. There's nothing wrong with that. It's just that having a nice little class that I wrote myself, and it's in a directory, and it's got a nice name, and it's easy to create, is my preference. I'd rather do that. Is mocking important? Yes, mocking is important, especially at the architectural boundaries of the system. And I'll say this, and I won't justify it, and you can do some more research on it on your own later. I prefer property-based or value-based testing inside a module and mock-based testing across boundaries. There are some people who want to do mock-based testing across everything. Every function is mocked. I don't do that. I do value-based testing, property-based testing inside modules, and I use mocks across boundaries. And by the way, those mocks speed everything up enormously.
Right. Next question. Brandon asks, recently Kent Beck wrote a tweet hinting that it's foolish to be proud of 100% test coverage. He compared it to being proud of reading every word in the newspaper. It sounds like Kent believes TD can be done without 100% test coverage. Do you agree with Kent?
I agree with Kent to the extent that 100% test coverage is an impossible goal to achieve, or a virtually impossible goal to achieve. I do not agree with Kent in his analogy. His analogy is that writing 100% test coverage is equivalent to being proud of the fact that you read every word in the newspaper. Well, you don't need to read every word in the newspaper. There's only certain articles you're really interested in. But you do need to know that everything in your code works. So the analogy breaks down pretty rapidly. Now, do I test everything with unit tests? And the answer to that is no. I can't test everything with unit tests. There are a whole bunch of behaviors in systems that are not immediately testable with other code. And the obvious example of that is stuff on the GUI. It's very difficult, if not impossible, to write a unit test that makes sure that you have displayed something properly on a screen. That doesn't mean I don't test it. I just have to test it with my eyes. My eyes become the unit test. I am very careful, however, to separate the things that can be tested from the things that are very difficult to test. And there is a pattern here that is very helpful. It's called the humble object pattern. If you can look this up on the web sometime if you'd like to. The humble object pattern is the way that we separate the things that are testable from the things that are difficult to test. And they typically occur at physical boundaries to the system, on the screen, or at a device driver, or at some other kind of physical boundary. That's where it really gets difficult to test. It's also difficult to test things where you don't know the answer up front. Sometimes you write code that's entirely speculative, and there's no way to write the test first because you don't know what the answer is. So then you can't write the test. You have to write the code first. And sometimes you can write a test after the fact. Now, having said all of that, I will come back to the point and say that the vast majority of the code that you write, you do know the answer to. and it's not hard to test. And you can write those unit tests, and for all that code that you can test, you should. One more point. I do not test every single line of code explicitly. Quite a bit of code can be tested indirectly. So, for example, getters and setters. Getters and setters do not need independent tests because the getters and setters will be called inside functions that I am testing. So they get tested. They just get tested indirectly, and that is sufficient for me.
Okay, so there's a lot of questions. Unfortunately, we're not going to have time for all of them, but there is one that stands out, and I guess it's somehow related to your recent blog post. And he says it's by Nick Harman, and he asks, you stated that a compilation error is also a failure. In Kotlin, trying to access a property of something that's nullable, you will get a compilation error. What is your final decision on features like null safety in Kotlin? It does take away the need for writing some tests. The language tests it for you.
So this is a very long discussion, and I can start that. First of all, I wrote a blog because I was concerned about the trend in modern languages like Kotlin and Swift, and there are many others, which seem to be encroaching ever further into static type checking. And I think that's a trap. And the reason it's a trap is that static type checking couples you to the compiler. The code is deep. The more you statically type check, the more deeply coupled you are to this compile time checking. And you are coupled to the invocation of the compiler across module boundaries. It's very difficult in a strongly statically typed system to create a small set of independently deployable modules. If you change one of the types, you have to recompile everything, and that becomes a bit of a problem. So I think we are moving, and maybe have moved across a balance point where we're going to have to pull back from again. Now, he said something else, which is that static type checking means there are certain tests you don't have to write. It seems that way. I understand why you would say something like that. I do not find that to be correct, however, because when you're writing unit tests, you are not testing types. You are not testing that you passed an int into a function. You are not testing that you passed an employee data structure into a function. What you are testing instead is a behavior of the system, that the function operates on that employee properly or operates on that int properly. And that is not something that a type can specify. A type specifies a constraint in the format or structure of the data, but not on the operation. And unit tests are always tests of operations. So in a unit testing environment, if you test all the operations, you are indirectly testing all the types, but you don't explicitly do so. So I don't believe there are any tests that you can avoid by adding stronger and stronger static typing to your languages. You will still have to write all the unit tests you would otherwise have had to write.
I think I have a follow-up question to this. So one of the big points you're making, and I'm just not getting it, is that whenever you change a type somewhere, you have to recompile everything because the interface of your module changes. Is that
Yes.
correct?
Yes.
Yeah. So, but if the type there makes any sense, this is what you have to do because all the other parts of the system have to have to account for this contract that has changed. So it's inevitable anyway, isn't it?
It is inevitable that two modules that share a type have to agree. That's what's inevitable. If the compiler enforces that agreement, then the two modules must be compiled. If the compiler does not enforce that agreement, it is possible to write code in one module that makes the agreement possible. Dynamic type checking, and by the way, I'm never opposed to type checking. Type checking is a good idea. My problem is where the type checking occurs. Does it occur in the compiler or does it occur at runtime? And certain amount of compile time checking is a good idea. Too much causes this compile time coupling. If we check our types at runtime, some of the really interesting details of our types at runtime, we can get away from having to recompile the world whenever a type changes.
Well, to be fair, we very rarely recompile the world when the type changes. We often recompile the immediate clients.
If you're recompiling, if you can isolate the boundary of types, so the types only exist within certain modules, and modules don't share those types, then you can enforce that type safety a great deal, because you're going to be recompiling that module anyway. If, however, the types span multiple module boundaries, if the types are known to many different modules, then a change in type causes a complete rebuild. And a complete rebuild means a complete redeployment. And I would like to avoid that. I don't want to be doing massive redeployments. One of the reasons that people got really enthusiastic about microservices is that microservices create this blockage in the type checking wall. When you communicate from one microservice to another, all the types disappear. And you're suddenly talking across this REST API, which is essentially a string. And it's all dynamically typed. And then, of course, on the other side, you reconstruct the data that you wanted. And everybody got very excited about that because it's decoupled and it's independently deployable. What they didn't realize is what they were doing was simply trying to escape from the type checking. And that you don't have to do it in microservices if you've got a language which is a somewhat forgiving with types. This is a very interesting and very long-winded philosophical argument on where our languages ought to be. And it is my opinion that we do not want to push our languages too far down the static typing route.
Okay, yeah, since I'm anyway here, I totally agree that it's largely a matter of opinion, and yeah, there are people who advocate for less types and for more types, and the balance point is somewhere out there, and nobody can be sure where that is. So it's like every person's intuition as of where it actually is.
If you take the last 40 years and you integrate it, you will see that the type checking of languages oscillates back and forth across a point. And you go from C, Algol to C to C++ to Java to Pascal. All of these languages oscillate back and forth. And the reason they oscillate is that there are bad things that happen on either side of the center point. And so there's this reaction. Oh, there's too many types. We need Ruby. Oh, there's too few types. We need Swift. And we keep on going back and forth across this point. And my blog was an observation that the pendulum has swung again, and it's past the center point, and we're going off into the again, not for the first time, but again, into the strong static typing realm, which we will have to pull back from because it's painful.
Yeah, well, I see your point, and I think that there are actually languages that far beside the balance point. Like there are actually languages where you don't need to do any testing because they allow you to verify the behavior with the types, dependently typed functional languages. But those are so far from what anyone would like to program that we are not even considering them in the mainstream.
Yeah, those languages become Turing complete at compile time. And then you have to wonder, well, okay, what is the execution platform? Is the compiler the execution platform, or do we want to actually execute in the running machine?
It's very often actually the other way around. They become Turing incomplete at the runtime because they have to limit the power of the formulae in the types so that they terminate. So they are often Turing incomplete indeed. Yeah, but there are variations where they sort of smuggle the Turing completeness back in. Yeah.
The computer has become Turing incomplete. The compiler is now Turing complete. What a wonderful idea. What a wonderful idea.
it all depends on what you want to spend your money on, like being really sure that it works correctly, or being able to do anything you might not need actually to do.
Okay, so we're past the hour. I find this discussion very interesting, and Uncle Bob, if you ever want, I think it would be fantastic to have you and Andre on another webinar discussing some of these points. So, you know, the door is always open for you whenever you like.
Oh, I'd always be pleased to do that.
Awesome. So we'll try and schedule that for some time in the future. But we are past the hour and we don't want to keep people waiting. So I very much want to thank you for coming on and for everyone hanging out. And let me just switch over to just put up the final slide.
And I'll take the time to say thank you to Uncle Bob. It was very interesting, both the presentation and the discussion.
Thank you very much. I had a lot of fun.
Thank you. Yeah, thank you very much, Uncle Bob and Andre for being on. So if for everyone else, we will be recording this. Well, it has been recorded and we'll be publishing it on JetBrains TV on YouTube. And if you've signed up and you've registered, we'll be sending you the link. So once again, thank you very much for doing the presentation, Uncle Bob, and for everyone for having attended.